Considering the daily motion of the night sky, we come to a profound issue that's at the heart of the Copernican revolution. How do we know that the Earth is actually in motion around the Sun, rather than the other way around? To our perception, it appears that the night sky orbits over our head, that the stars are on a celestial sphere, a cap over our heads, orbiting once every 24 hours. The relativity of this situation is actually quite profound, and it turns out it was not for a few hundred years after the invention of the telescope that we proved that the Earth was moving around the Sun, by a phenomena of stellar aberration, where starlight is deflected slightly in its apparent path to the Earth by different amounts as the Earth moves around the Sun in a year. For general purposes, though, we can consider the night sky to orbit over our heads. The diurnal or daily motion of the Earth is of course caused by the Earth's spin. Knowing the size of the Earth, we know how fast at any point on the Earth's surface we are moving. This speed is more than 1,000 miles at the equator. At a mid-latitude, it's a few hundred kilometers per second, and it's zero, of course, at the poles. This is why, for example, spacecraft are often launched in the United States from Kennedy Space Center at the southernmost latitude. The Europeans actually use French Guiana, which is very close to the equator. The north and south celestial poles are defined as the projections of the Earth's poles onto the celestial sphere. There is a relatively bright star, Polaris, near the north celestial pole, but no analogously bright star in the southern hemisphere, which is why southern hemisphere navigators use the Southern Cross and project the Southern Cross several times its length towards the south celestial pole. Navigation just a little trickier in the southern hemisphere than the north. The celestial equator is the projection, in an imaginary sense, of the Earth's equator onto the celestial sphere. It's also significant that we can define two different days. We can keep time by the sun or by the stars. A sidereal day, or a day kept time by the stars, is 4 minutes shorter than a solar day. Due to the Earth's rotation, stars rise in the east and set in the west. Depending on our latitude, some stars are circumpolar or always appear in the night sky, regardless of the time of year. Some stars are invisible in some parts of the Earth's orbit, and some stars are invisible because they're in the other hemisphere of the Earth. If you think about it conceptually, if you're doing your observations from the North or South Pole, you would be able to see the same 50% of the night sky over the course of a year, and the other 50% of the night sky would be always invisible to you. To see the difference between solar and sidereal timekeeping, or solar and sidereal days, let's imagine the Earth in its orbit of the Sun. The Earth is spinning in the same sense that it orbits the Sun. A solar day is the time it takes between one Earth orbit for the Sun to appear overhead or at its highest elevation in the sky. A sidereal day is the time it takes between an orbit of the Earth for a star to appear at its highest elevation in the sky. When a star or the Sun or any object is at its highest elevation, we call it its transit. If we think about the Earth in its orbit of the Sun, then a sidereal day must be slightly shorter than a solar day, because that same star will appear fixed overhead while the Earth has moved about 1 degree in its orbital plane around the Sun, adding 4 minutes to a solar day compared to a sidereal day. The consequence of this is that any star rises or sets 4 minutes earlier every day. And over the course of a year, those 4 minutes, of course, add up to 360 degrees, or 24 hours. And so the whole cycle of the stars of the night sky cycles every 365 days. If you want to look for a particular star rising or setting in the night sky, relative to the last time you saw it, you just have to calculate how many days ago it was and add that number of minutes times 4 to the time you go out and look for that star. This is the kind of celestial timekeeping that navigators do all the time. The final frame of reference for locations in the sky is not as important for navigation because it's a reference to the Milky Way, the very large system of stars that includes the Sun. The Sun is confined to the disk or the plane of the Milky Way galaxy, so when we see the ragged band of light girdling the Earth in the north above us and also in the south, the part of the world we can't see, this represents the plane of the galaxy. It turns out that the view towards the galactic center, the bulge of stars and the largest density of stars, is in the southern hemisphere, so people living south of the equator get a richer view of the center of our galaxy. The Milky Way is truly spectacular in the southern hemisphere, especially in a dark place like Chile, where the sky is truly dark. The daily motion of the Earth spinning on its axis every 24 hours, gives the appearance of the stars rotating overhead, rising in the east and setting in the west. Timekeeping is different based on the stars and the sun. Most astronomers keep time by the stars, and the sidereal day is 4 minutes shorter than the solar day, or the time it takes for the sun to go to its highest elevation on consecutive days. That means that any given star rises or sets 4 minutes earlier every day, and the entire night sky pivots through our available view every year.